welcome. My talk actually probably dovetails nicely with just the previous talk. It will be about a learner's journey in using Dask to help us speed up the production of our transit data set that we're putting onto the California Open Data Portal. So my name is Tiffany Chu. I'm a data scientist at Caltrans, which is the State Department of Transportation. Within Caltrans, where I work is a division called the California Integrated Travel Project. And this is a statewide initiative that started in 2018 to really modernize our transportation experience. Broadly speaking, our work touches on three things: standardized trip planning information, contactless payments, and automating customer discounts. And so I'll focus on the first, which is trip planning information today. So the bulk of our data in our warehouse is GTFS data, which is the General Transit Feed specification. It's all things about public transit service. And essentially, it's everything you need to pull up Google Maps and ask, I want to get from point A to point B using transit. How can I do it? So it's everything behind that. And that's what we ingest in our data warehouse. It's a very rich data set. We can answer a lot of things from it. One of the things that we answer is, where are high quality transit areas? So by statute, Caltrans is required to make this available. These corridors and these areas near major transit are areas that would get land uses that support walkability, density, and active transportation. So it's really important to know where these places are. And we've been required to make this available for the last 20 years, and we haven't really been able to until now. But now that we have GTFS data and GTFS is public, it just makes sense that as we're kind of deriving these outputs from it, we also make that publicly available. And that's why we put it onto our open data portal. So why now, you ask? Well, in figuring out where these areas are, it requires a lot of geospatial processing that we were doing in Python. And because we were working with transit operators in the state, it was big. And we wanted to make this data available frequently. So right now we're publishing on a monthly cadence. And so Dask integrated nicely with our existing workflow because first it integrates with Python. And as a big data tool, you're not going to have the memory issues that you might run into with pandas. The fact that each run was taking 10 hours a month, combined with the fact that we wanted to run this very frequently, meant figuring out a way and a solution that would make this sustainable in the long run. And so I didn't want to tie up my own computing resources for 10 hours a month. And so I kind of embarked on this effort to really scale and to optimize. And I found that the most valuable thing that came from using Dask was it forced me to think about what step was sequential, what step didn't need to be sequential, and could be parallelized, and really kind of modularizing the code so that we could keep using our outputs in a smarter way. When we're working with large data sets, sometimes we use loops as this convenient way for us to avoid having memory issues or crashing your kernel. But loops become this way of imposing a sequential framework. And what I mean by that is, we're doing something to transit operator number one. We finished and we move on to number two, then number three, when the order doesn't matter and we could really do the same kind of processing simultaneously on all the operators at once. And so that makes it perfect for, using Dask because we're able to kind of move things away from sequential. Our version 1 it was 10 hours. It just used pandas, but even simply switching over to Dask data frames helped us cut the time down in half. And then a later iteration really focused in on what things are we leaving sequential and how could we remove it. But it's very iterative. And so now on the horizon is, well, we've been doing this locally on our local cluster. Can we move it to the cloud cluster? And it makes sense now to set one up. So I'm going to walk through some of the text of the legislation and help translate that into maybe more discrete code concepts that we can use. So the definition of a high quality transit corridor is a corridor with fixed route bus service with service that's at least 15 minutes during peak hours. And the idea of corridors is very nebulous. So we bring in this concept of equally sized line segments. No longer than 15-minute service simply means every hour we see at least 4 trips pass by at that stop. And if there's like multiple stops on that same segment, we'll keep the stop that has the highest number of trips. And for peak hours, we'll deal with the day in 2 time periods. So before noon and after noon, and see which hour has the most stops, or sorry, the most trips that hour. And so kind of show you how all these concepts come into play. Our starting point here is the physical coverage of just one bus route. We start with this idea, and when we look at a bus route, we can understand like it travels eastbound, it travels westbound, and in GTFS, this would be captured in 2 rows with 2 different shapes. But if we bring them together, we get this top navy line. And we can immediately bring in GeoPandas and Shapely to help cut this line into segments and figure out, does this segment run east-west or north-south? And then with Dask, we can look across all the segments for that route and say, this route is now, it's an east-west route, or it's a northwest route, north-south route. And with Dask, we have to bring in a pretty big table. It's big because it has a row for every time a bus makes a stop. So if it arrives at a bus stop, there's a row. And we use Dask to parse the timestamp, which comes as a string. And we figure out what departure hour what departure it is in, and we can count for this stop in this hour how many trips took place. And we can look across all the hours, in the AM and say, okay, at this stop, what was the highest number of trips that were made? Then we bring in Dask GeoPandas to do our spatial join. So stops are points, they have lat long, and they need to be attached to segments. So we'll draw a little buffer and we ask, where does this point fall into this kind of elongated polygon now? And if there are multiple stops in a segment, we'll just keep the one that has the most number of trips. And with that, we can very easily see where are there for more than 4 trips an hour. And that is flagged as being, yes, it is a high quality transit corridor. So the next concept we bring in is, well, what's a major transit stop? What I will skip today is the fact that rail, ferry, bus rapid transit is also part of this definition. But I'll focus on the most geospatially complex, which is where there is an intersection of 2 or more major bus routes with at least 15-minute frequency during peak hours. And we will use that idea that we just figured out of these segments and figure out, all right, which 2 intersect each other. And immediately you're probably thinking GeoPandas clipping, GeoPandas overlay. That's probably the idea I want to use. But let's dive a little deeper and ask, what do we really mean when we say they intersect? Yes, we mean these two routes touch, but we also mean a lot more than that. And so in this diagram here, you can see that there's 3 bus routes at this street intersection. And when we think of 2 routes intersecting, we only think of Route A and Route C as intersecting. We think of Route B and C as intersecting, but we do not think of routes A and B as intersecting. And why is that? It's because Route A and B run in the same direction. So technically, their lines would basically run on top of each other, they touch, but we don't think of that as an intersection. And so there's 2 ideas that we can glean from this picture. The first is geography matters. The routes have to be close to each other in space. So routes in Los Angeles are not going to run into routes in San Francisco. And the second idea is direction matters. So specifically, perpendicular directions, if they run perpendicularly to each other, they're allowed to intersect. So what can we do with these 2 ideas to help us? Well, what we'd like to create is this pairwise table where we say, like, okay, this east-west route intersects with this north-south route. But there's so many combinations, like, how can we do this? Clipping is very expensive. We don't want to try all the combinations out there. So Dask GeoPandas, which does not have overlay, but does have clipping and spatial join. So we use the idea of spatial join with Dask, which is we ask, do these 2 routes intersect? Yes or no? It doesn't tell us that area of intersection. That's not what a spatial join does, but it tells you yes or no, they intersect or no. And with that, we're able to quickly narrow down to just the valid pairs that we'd like to cycle through in order to find the area of intersection. And what this actually leaves us with is over 100,000 pairs. And so if we're not doing this and we're just trying all the combinations out there, we're really trying a number that's magnitudes greater than that. The next thing is, in a version 3, okay, in this pairwise table, I'm noticing that I only keep east-west routes with north-south routes. But how I was implementing that was I was trying all these combinations and then removing rows where the direction was the same. And version 3 really brings that second idea of direction to the forefront to say, wait a minute, I don't need to remove it after the fact. Why don't I just allow east-west routes to be spatially joined to north-south routes to begin with? And that does it in a much simpler, cleaner, clear way. And once this whole pairwise table is set up, I actually end up moving away from Dask because all this work has lent itself to use GeoPandas intersection really nicely, which is it just does a row-wise comparison and it gives you that area of intersection between the 2. And that's exactly what we want. So here's some code. It is supposed to be illustrative and not to be overwhelming. But in version 1, it's cycling through kind of all the combinations out there to do the clipping. It's trying a lot of combinations that end up not adding anything to our results. And so the step takes hours and we need to do something different. In version 2, this idea of geography comes into play. So this idea of like different operators being in different areas is much easier to figure out because you have, very different regions in the state. And you can quickly figure out which ones might touch each other or intersect each other. But for routes within the same operator, they're basically running in the same service area. And so it's still looping through to try all the combinations because chances are a route in Los Angeles intersecting with another route in Los Angeles, it's pretty high. So this, it's better. It's less than an hour, but we can do better. We must. And so here, version 3, it brings that second idea of direction into play. And it just says, all right, in my spatial join, you have to be in different directions, and I'll spatially join you to figure out if you're ever valid. And then quickly, I'll throw you in with GeoPandas to find the area of intersection. This is really fast. It's really clean. It's really simple. It takes less than a minute. And so here's kind of our result. This is what's put on our open data portal. This is San Diego, and we have a couple of different types of what qualifies, and this is what we'd like to make available to the public, at least on a monthly cadence. And so what were my lessons learned? Well, first, we should use a big data tool like Dask to handle memory issues, not loops. So in version 1, you probably need loops to just get some visibility into what you're working on, to make sure, what you intend to execute is actually being done. But don't leave them in place simply just because you don't want to crash your kernel. Use the right tool to handle like a memory issue. And the second thing is, well, more on that. When we leave loops in place, we leave things to be sequential when they need not be. They can be done simultaneously. They can be done in a parallelized fashion. And, trying to think of ways to remove loops really forces us to think, are we doing this in a really thoughtful way? The second lesson is, well, rewrite. I mean, I cannot emphasize this more. Rewrite. For me, this workflow was the first time I ever used Dask. And so it's this whole suite of tools. It's like a grab bag. I didn't know where to begin and what to use. But every time I rewrote, I got to use more and more of the tools and kind of look at what bottlenecks remained, what were the pain points, and what can I use from this whole grab bag that can address the pain point that remains. And right now, like all the things I've talked about, the gains and time, like they're all done locally, but now the code is much more set up for moving it to the cloud. And the last lesson is, well, sometimes the best optimization you can do is really going back to the basics and trying to get the most out of your pre-processing steps. And so I found the exercise was trying to match what I was writing in my code with how I was talking about it. How was I explaining it? A lot of times we write in a more complicated way than how we would explain it, and bringing that together and simplifying the code to match exactly what I was saying was really critical. And if that meant moving away from Dask, that was okay. I can mix and match and use the different tools I needed. I didn't need to stay only in Pandas, only in Dask, but I could just mix and match in every stage. And that's a wrap. So I've left my team's GitHub here, as well as contact information and a site for all of the analytics work that my team is also working on. So thank you.
Thank you for this awesome talk. I'm sure we've learned a lot, and any questions are welcome. We have a question. What other technologies did you consider?
So for us, we just considered Dask, and it played well with basically our data warehouse and our hub. So our Jupyter Notebook environment is in a hub, it's in the cloud, and we're connected with our warehouse, which is BigQuery. And so Dask had the other, I guess, all the ways that we could connect from where our data was, how we were working on it easily. And so we just started with Dask.